Hello, I'm Ryan Baker, and this is Big Data in Education. Today we're going to continue our discussion of classifiers. Classification is where there's something you want to predict called the label or the predicted variable, and that something that you want to predict is categorical. The answer is one of a set of categories, possibly 0, 1, and not a number. In a previous class, we discussed several algorithms for classification, including step regression, logistic regression, and J48 or C4.5 decision trees. Today we're going to discuss more classification algorithms, starting with decision rules. Decision rules are sets of if-then rules which you check in order. So in other words, you check the first rule. If the first level is true, go with the answer. If it's not true, take all the rest of the data and consider that within the second rule. Within that second rule, if the answer is correct, go with that. But if the rule is not correct, then go on with the remaining data. So for example, if time is less than 4 and knowledge is greater than 0.55, then correct. So we take all the cases where time is less than 4 and knowledge is greater than 0.55. If they're correct, we're done. We take the remaining data and say, within that data, if time is less than 9 and knowledge is greater than 0.2, then we say correct. Now we take the remaining data and say, if num attempts is greater than 4 and knowledge is less than 0.33, then incorrect. And finally, we take the last part of the data and say, otherwise correct. So every time we operate a decision rule, we're taking part of the data and just saying, all right, we know the answer, taking the rest of the data and only considering among that. Like anything we discuss in this class, there are many algorithms for decision rules, and the differences between them are in terms of how the rules are generated and selected. The most popular subcategory, which includes the popular algorithms JRIP and PART, repeatedly creates decision trees, which we talked about a couple classes ago, and distills the best rules out of them. The path that you take in JRIP to generate rules from decision trees is you take a decision tree. If there's at least one path that's worth keeping, whatever that means, go to step 3, else continue on to step 6. For step 3, take the best single path from the root of the tree to the leaf of the tree, any leaf, and make that path a rule. And again, how best is defined varies between decision rule algorithms. Then you take all the data points classified by that rule, remove that rule from the data set, and go back to step 1, create a new decision tree, and classify within it. Eventually you'll get to a point where there's no path that's worth keeping in the entire tree. At that point we're at step 6, and we take all the remaining data points, find the most common value for those data points, and make an otherwise rule using that, where we just take all the data points we don't know what to do with and make our best guess just based on the base rate in the remaining data. Decision rules are relatively conservative. In particular, they lead to simpler models than most decision trees. Decision trees, at least J48, are already a relatively conservative algorithm. They also lead to extremely interpretable models, which is a difference from most other data mining approaches. They're good when multi-level interactions are common, just like decision trees.
Another algorithm is KNN, K nearest neighbor. This predicts a data point from the neighboring K data points, and it takes the most common label among those K points. So take KNN with K equals 5, for example. Here we see a group of data points. Some of them are blue, meaning one group, and some of them are orange, meaning another group. We get a new data point, and we want to know, should we predict that it's blue or orange? So this is K nearest neighbor with 5 neighbors. So we're going to look at the 5 nearest neighbors, which turn out to be these 5 data points. 4 of them blue, 1 of them orange. So what do we say? We say it's blue with 80% confidence, because we have 4 to 1, 4 out of 5, 80%. So this data point is blue.
Now let's talk about K-star. K-star is an instance-based classifier that predicts a data point from neighboring data points. It weights points more strongly if they're nearby. So let's take an example. Let's say that we have these data points with blue and red. And you can see that blue and red kind of each have a region, but there's not an easy way to say, oh yes, it's exactly this. Now let's say we need to classify a new point, the green point. To classify the green point, we look at every other point and its distance from the green point and weight in favor of the closer points. So you can see here that the circle, kind of a close circle around green, only has blue. As we get out a little further, we get some red. But compared to the initial blue set, we're still not all that much red. K-star is good when the data is very divergent, when there's not easy patterns but there are clumps. Lots of different processes can lead to the same result. And it's kind of intractable to find general rules. But data points that are similar to each other tend on the average to be from the same classification group. from the same class. A big advantage to K-star is that sometimes it works when nothing else works. My group in specific has found that it's useful for detecting some emotions from log files, where there's many different ways that emotions can manifest itself within a student behavior, and they may not be all that related. But the big drawback is to use this model, you need to have a whole data set, which makes it sort of intractable for use in a running educational system. If you imagine having to have 1.6 million data points that your system has to go through every time it wants to make a decision, that doesn't work too well. On the other hand, for kind of offline analysis and discovery of models analysis, it can be a very powerful tool.
So that wraps up this lecture. In later lectures, we'll discuss goodness metrics for comparing classifiers, validating classifiers, and classifier conservatism and overfitting. In the next lecture, a case study in classification. Thank you very much. I'm Ryan Baker. This is Big Day in Education.